In this video, we're going to look at maxima and minima of functions, and another way to describe that is to find the extrema of a function. And we're going to look at it on an open interval, and we'll look at it on a closed interval. And there's a few definitions here, but before we even go over those definitions, I want to look at the picture. So I think the picture will help you understand what we're trying to accomplish here. And there's also a link here. There's an interactive figure that you can play around with. You can click on that link when you're not watching the video. But we're just looking at a function, and we'll just think about this function on the closed interval from a to b. And we've got these interior points c, e, and d, x values. And at C, we have what's called a local maximum. And what that means is that there's no greater value of f, right? There's no greater value of the function, which is your y value, nearby. So we're talking about, when we say locally, we're talking about just in a particular area. Right? And at E, we have what's called a local minimum, and that would be the smallest value of f, again, nearby, right? A local minima. And at B, we have another local minima. It's the smallest value in that area, or the smallest value of f nearby. So now we have what's called an absolute max and an absolute min. And so even though at D we have what's called a local max, right, that value right there is the largest value in the neighborhood, or in the nearby. But it also happens to be the largest y value of the whole function on this interval. That's the greatest y value. And at A, we actually have a local minimum. Even though it's at an endpoint, that's okay. It is the smallest value nearby, but it also happens to be the smallest y value overall. So the absolute max and absolute min have to do with the greatest value and the smallest value of the whole function on an interval, where local max and local min are just the greatest value and the smallest value of the function for a little neighborhood. And we're going to look up here at these definitions. So the definition of a local max at some value x is basically when f of c is the largest value in an interval. All right. And the local min is when f of c is less than f of x for all x in an interval. Right? And local maxes and local mins come under this general category of local extremum. The other thing we want to talk about is a critical value. And the definition of this, the critical value for a function f is a value in the domain of f where the graph either has a horizontal tangent or where f is not differentiable. So either f prime is equal to 0 or f prime is undefined, right? Those would be considered critical values. And the critical value where f prime of c is equal to 0, that's also called a stationary value. So let's look at some examples. In example 1, we just want to find the values of x for which the following have local extrema, and we also want to find the critical values. And so we'll start by looking at this first one. It's a parabola, and it actually happens to be the graph of y equals x squared. The critical value is where the first derivative is equal to 0. And so what we're looking for is there a value of x where you have a horizontal tangent? So just take a few seconds to look at that picture and choose the x value where you have a horizontal tangent. Okay, and hopefully you said x equals 0, so that's where we have our horizontal tangent. And now we want to find out, is there a local min? So a critical value is an x value. A local min or a local max is actually a y value, or function value. So the local min, there is a local min, and that local min is 0. The smallest value in the neighborhood here is y equals 0. So we have a local min, and it occurs at x equals 0, but the local min is y equals 0. So the smallest value of the function in that area is 0. It occurs when x equals 0. There's no local max because this function goes to infinity as x goes to as x gets larger and as x gets more and more negative. So there's no local max. The next graph happens to be the graph of y equals x cubed. And again, it really doesn't matter to answer these questions, but critical values are where you have either your first derivative is undefined, but also it has to be in the domain of the function, or where you have a horizontal tangent. And so if we look at this function, we can see that we have a horizontal tangent at x equals 0 again. So our critical value is x equals 0. We look at local min here. This function does not have a local min. We're looking for little peaks or little valleys for local maxes and local mins, and this function does not. It flattens out here and then it increases again. So there's no max or no min. Let's look at the third scenario here. And again, this function looks like some type of cubic function. I'm not sure. I don't have all of the information. But on what I can see in front of me is that I would have a horizontal tangent right here and right here. So our critical values are x equals -1 and x equals +1. I have a local max right here. Right? It's the largest value in an area, and that local max is 5. So the local max occurs at x equals -1, but the actual maximum value in that area is 5. So we have a local max of 5, so y equals 5. That is your max. It occurs at x equals -1, or occurs when x equals -1. We have a local min right here at x equals 1, but the actual y value also happens to be 1. So the local min is y equals 1, and it occurs at x equals 1. So it's important to distinguish between where the x value, where the minimum and maximum occur, and what the actual value of the minimum and maximum are. All right, let's look at the last scenario. We have a critical value. It appears at x equals 0. We have what we call a cusp. So we can tell from the picture that the first derivative is undefined. So our critical value is going to be x equals 0. It also looks like we have a local min at x equals 0, but the value of that local min, a little hard to see here. I would say it's approximately 3 or 3.5. Not as clear on this graph. So let's assume it's 3.5 here. So we have a local min of 3.5, and it occurs at or when x equals 0. And we don't have a local max if we're assuming that this function is going to continue. I'll put little arrows on there. We don't have a local max at this point. At this point, I just want to summarize what we just found. So in the first picture, we have a critical value, and we have a local min, a local max. We have a critical value in the second picture, but we don't have either a local max or a local min. In the third picture, we have critical values, and we have a local min at one of them and a local max at the other. And in the third picture, we have a critical value, and we have a local min but no max. And let's look at this statement. Local extrema occur only at critical values. What this means is that if any local extrema exist, they will occur at a critical value. Now, it doesn't mean that if you have a critical value, you are guaranteed to have a local extrema. But it does mean that if you have a local extrema, it has to occur at a critical value. And a little side note that extrema is the plural and extremum is the singular. So this statement, if f has a local maximum or a local minimum at x equals c, then c is a critical value. All right. The other word that can be used to describe local extrema is relative, and so some textbooks use relative extrema instead of local. So if you see that word, that's what they mean. And the first thing I want you to be able to do is to just find critical values. And so we'll do that in the next video.